Okay? So this should give you a good hint as to why these are different from these. Most of these don't have little circles, and these ones do have little circles. So probably having a binary companion can do something to these pulsars, which makes them end up in this region of the diagram instead of just going off into this pulsar graveyard. Okay? So what we think is that the pulsars in that lower left region of the diagram have been recycled from a companion star. I'll show this movie again. So what we think is happening is that some pulsars, when they go into the graveyard, their emission shuts off. If they have a companion star, though, this companion star can give angular momentum and material to the pulsar and spin it back up again and bring it back to life. So these pulsars, let me just go back to here and then I'll show this again. These pulsars in this region of the diagram have gone into the pulsar graveyard. They've died, and they've been resurrected by a companion star and been spun back up to very, very short periods into this region of the diagram. Okay? So in this movie, we start off with a red giant star and a regular star. The red giant star explodes in a supernova explosion and leaves behind a pulsar. Now you can see this pulsar was spinning pretty slowly, but now its companion becomes a red giant and it starts spinning it up. So this pulsar is spinning faster and faster and faster and becoming one of these millisecond pulsars. Now it's spinning very, very quickly. In this particular scenario, this second star also explodes. And now we have two pulsars in orbit around each other. And we only know one such system which looks like this. Most of the time, when the second explosion happens, the system is broken up, this star goes hurtling off that way, and we're often left with just an isolated pulsar. Okay? So at the end of a process like this, we typically will have a millisecond pulsar and a companion. And all the systems we've seen with millisecond pulsars generally have more or less circular orbits, because we think this spinning out process tends to circularize the orbit, so they're more or less circular. And this will be important later on. OK, so let me leave that sort of general introduction. And I just want to talk a little bit about a couple of projects that we're involved in, a couple different surveys for new pulsars and studies with pulsars, just to illustrate some of the neat things that we can do with pulsars. You'll notice that throughout I've been mostly referring to radio observations and radio pulsars. Pulsars can actually be detected across a pretty wide range of the electromagnetic spectrum. So this is the electromagnetic spectrum. Here we have really high energy gamma ray photons, very low energy radio photons. You could think of it also as radio photons have very, very long wavelengths, and gamma ray photons have very, very short wavelengths. Here's the visible part of the spectrum, which is really tiny. Okay. So most pulsars, we can't see invisible light at all. We know of about 2,000 of these. However, if we look in the night sky, we can't see a single one of these pulsars with our eyes. Right? They're just not bright, invisible light. It'd be pretty cool, I think, if we could, but we can't. And it just so happens that they're most easily detectable, for the most part, at radio wavelengths. So we use radio telescopes to study them. We can also do lots of studies in the X-rays and gamma rays of the pulsars as well. But generally, we study them at radio wavelengths. OK, so radio wavelengths are really long. So when we think about radio waves, they're sort of anywhere from this size to this size or even much bigger. Okay? Something like the size of a football to the size of a football field or so. And we need really big dishes to study radio sources because they're very, very, very weak. Okay? If you look at all the energy from all the pulsars we've ever discovered, since the discovery of the first pulsar, it would be less than the energy we need to power a light bulb for, say, 10 seconds. Okay? They're very, very weak objects. So here are some of the telescopes we use to study them. Of course, here's the GBT, the Green Bank Telescope in West Virginia. If you haven't been there, I strongly recommend you visit. It's a really neat place to visit. This is a 100-meter telescope. This is the Lovell Telescope in England. Here's the Arecibo Telescope in Puerto Rico. This is the largest radio telescope in the world. Here's the Parkes Telescope in Australia. This is a 64-meter telescope. Okay, so I'm just going to discuss 3 projects that we're currently doing with pulsars. Okay, the first one is a survey with Arecibo. This is this telescope in Puerto Rico. The second one is a survey with Green Bank. And the last one is a project called the Pulsar Timing Array, where we're using an array of pulsars in the sky to do some pretty neat stuff with Einstein's theory of general relativity. Okay, so the Arecibo survey. Okay, so this is the largest radio telescope in the world. It's actually under threat of closure from NSF budget cuts. So if you're as worried about it as me, you can go online, and there are some nice petitions you can sign to try to keep this telescope going for another 10 years or so. This telescope has done a lot of really good pulsar work over the years. We're involved in a survey with this telescope for new pulsars. The reason this survey is really exciting is that the Arecibo telescope now has a 7-beam receiver, which means we can look at 7 parts of the sky at once, and we can detect 7 times as many pulsars, or conversely do a survey 7 times as fast. So this survey is called the P-alpha survey. Pulsar Arecibo L-band feed array. Doesn't really matter. We've been processing this survey here at WVU. So far in total, we've found about 46 new pulsars. This is a collaboration with a couple other universities as well. There's a couple really neat new pulsars that we found with Arecibo. We found a really neat binary pulsar that's very relativistic, which means it's moving really quickly. We found a pulsar that's young, that's associated with a really bright gamma ray source. I don't want to talk about either of those, though. What I'd like to talk about is a binary pulsar system that we found last year. It's in an eccentric orbit. Okay? So what do I mean by eccentric? I mean not circular. So an orbit that's not circularized. And this is pretty strange because in our standard model of how these pulsars are spun up, we think that this spin-up process circularizes the orbit. Every other millisecond pulsar binary we found has been in an extremely circular orbit, and this one is not. And we still have no idea why. Okay? So what we can do is we can look at the period of a pulsar over time, and we can see this binary motion, which is causing the period to change. We can see a couple other neat effects, and I don't want to get into too much detail. But this pulsar has a spin period of about 2 milliseconds, okay? So this pulsar is spinning really, really quickly, okay? It has a really large eccentricity, though. Its orbit is not nearly circular, and this is really strange. Another strange thing about it is that it's really massive. We can actually measure the mass of the pulsar by looking at the binary motion, and it's much more massive than what we think a pulsar should be. We can actually take optical images, and we can see the star that is this pulsar's companion, even though we can't see the pulsar itself. So that's pretty neat. So here's the Earth in the Sun orbit. It's a little bit eccentric, but it's pretty circular. And here's this pulsar in its companion's orbit. It's in a very eccentric orbit, not circular. And we're really puzzled as to how this type of thing could form. So the main reason I'm showing this discovery is just to illustrate that even though we found the first pulsar in 1967, right, so over 40 years ago, we still don't understand really basic things. We're continually finding new objects that completely challenge our assumptions of how these objects form, okay? We don't think this thing could have been born as it is. We think that's pretty unlikely. Could it have been in one of these globular clusters, and could it have captured this companion in exchange interaction? It's possible. Maybe it has a triple companion. Maybe there's some other planet in the system that's keeping this orbit a little bit eccentric. All of these things are possible, and we're still trying to figure this out. But this is a paper that was published last year in Science. Okay. So another survey I'd like to talk about is a survey with the Green Bank telescope. So 2 summers ago now, the Green Bank telescope was shut down for repairs. It needed to have its track refurbished. Okay, and that sounds like bad news for most people, but we were actually really excited because we were going to be at Green Bank all summer, and we decided that while the telescope was just sitting there, not really doing much of anything, we would just take data in whatever direction the telescope happened to be pointing and just search for new pulsars in those areas of the sky. So we did that. We covered a lot of sky. We covered about 30% of the sky that's visible from Green Bank. One of our grad students, Jason, has been looking at these data. We found about 21 new pulsars so far. Okay, and so this is the most sensitive large-scale survey for pulsars ever done. Okay,